Hey everyone. So in this video, I'd like to say a few more things about function composition. So we said that to compose two functions, what we do is we take the output of one function and use it as the input for the other. And so the way we express this, if I got two functions f of x and g of x, I can write their composition as f of g of x. This means take the output for g and use that as the input for f. And another way we can express this same idea is to write f composed with g of x. Again, this means to input into g and use the result, use the output as an input for our f function. Right? In this sort of notation, we sort of work inside out. And so in the last video, we also talked about composing two functions as equations. And so here I'd like to practice that a little bit more. So here I want to compute g composed with h of x using these two functions below. And so if you're feeling up for it, please go ahead and try these problems out first, and then we can talk about them afterwards. And so this tells us to use our h function as our inner function to input this into g. And so what this looks like is, I take my g function and I input h into it. And so wherever I see that input variable, I'm going to replace that with my function h of x. So here, x, my input variable, I'm replacing with h. And then again, my input variable in the denominator, I'm replacing with our function h of x. And I'm adding 1. And so what does this come out to be? Well, h of x is 4 over x. And so this is kind of a messy function to look at. There's fractions within fractions. And one thing we can do to sort of simplify this, rewrite this in a friendlier way, is to recognize, well, this is a fraction, and we can always manipulate fractions by multiplying the same quantity to the top and the bottom of the fraction, in the same way that we can reduce a fraction by dividing the same number to the top and bottom of a fraction. And so something I can do that'll clean this up is I can multiply the numerator and the denominator by x, right? That's the same thing as multiplying by 1 over 1, right? Because x over x is the same as 1. And the benefit of this is that, well, in the numerator, right, we have this division by x and this multiplication by x now. And so those two undo each other, right? Division by and then multiplication by the same thing really amounts to not doing all that much. So we're just left with 4 in the numerator. And then what do we get in the denominator? Well, here we're taking this x and we're multiplying it, we're distributing it to this pair, right? We're multiplying it to this entire denominator. And when we multiply it to 4 divided by x, just like what we saw in the numerator, well, we just get 4, right? To take 4 and divide it by x, and then to multiply by that same number x, just leaves us with 4. But then when we multiply x with this next term, with 1, well, we're left with x, right? So g of h of x, it's really the same as the expression 4 over 4 plus x. Okay, so let's go over another example of composition. Here I want to determine the composition g of f of x for these two functions below. Again, if you're feeling up for it, pause the video and give this example a try, and we'll go over this in just a moment. So here this time the inner function is our f function, and so we want to input that into our g function. So wherever we see that input variable for our g function, we replace that with f, right? So g of f of x, and this is equal to 2 over our input squared, and so our input in this case, that's f of x. We're going to square whatever f of x is, and then subtract away 3. So this is 2 over, and so we're going to square, well, what are we going to square? We're going to square f of x is the square root of x minus 2. And so, if I take some quantity and I take the square root of it and then I square it, well, those operations are going to reverse each other, undo each other, and we're just going to be left with the inside. For example, if I use a number, let's say the square root of 9, and then I square the result, well, the square root of 9 is 3, and I square this, I'm going to get back 9. I'm going to get back the input I started with, right? Or the quantity I started with underneath the square root. And so here we can see that if I have 2 over the square root of x minus 2, and then I square it, well, that's just going to leave me with x minus 2. And then I still have the minus 3 afterwards. And so here I'm referring to that x minus 2, the square root of x minus 2 squared. And then what we get out at the end of the day here is 2 over x minus 5. So this is an expression for the composition of the functions g with f. And so one natural thing we can talk about or ask when we look at the composition of two functions, when we look at this resulting expression, is what's the domain of this composition? What's the domain of this new function we've created? And so, I look at this function, I look at this expression, and I can see that, well, the input value for this new expression should not be 5, right? So input should not be 5. This leads to division by 0. And so in the domain, I know that 5 is tossed out of this set of all input values. But is there anything else that we should toss out? Well, this resulting expression doesn't tell us that, but actually there are other values we should remove from the domain for this composition. Right, and so maybe just to justify this a little bit, if I imagine what's going on with the composition of two functions, we can kind of sort of visualize the procedure as, I'm going to take my my input value, I'm going to plug it into, well, in this case, our input function was f, right? So that was what we really input into first. So this comes out as f of x is what we're really going to input into first, and then we're going to take that result and then input into our g function, right? That's what composition means, and then our result is the result of our composition. And so this is the idea of the composition above. But if there's a number that I cannot plug into my f function, in other words, I couldn't have plugged into f to begin with, then it breaks this whole composition, and I'm not going to get a reasonable output out. And so if we look at our above example, is there anything I can't plug into my f function to really compute a composition for? Well, my f function is this square root function here. And what's the domain of this square root function? Well, it consists of the values such that x minus 2 comes out to be non-negative. Right, the domain of this part of this function here is anything that makes the inequality x minus 2 is greater than or equal to 0 true. In other words, x needs to be greater than or equal to 2. So these are the values that are okay to plug into our f function and will come out with a result in our composition, as long as it's not 5 as well. Right, x is not equal to 5 as well. So here, when we're trying to find the domain of a composition, what we need to do is we need to, here maybe I'll write that out. So to find the domain of a composition, here again, when we say domain, we're talking about the set of all input values for our function. Well, what we need to do is we need to look at the domain of the result of the composition. Right, so in this case, that's this part here. This 2 over x minus 5, that was the result of our composition. And so we saw that we can't plug in 5 from this resulting composition. And what we need to also do is look at the domain of the inner function. If there's something I can't plug into my inner function, it's something I can't plug into the composition. And so where the two overlap or where the two agree is the domain of your overall composition. Right, so earlier we said the domain of the result was any value that's not equal to 5. And we said that the domain of the inner function, well, that's x is greater than or equal to 2. And so pictorially, if I look at a number line, then here's an x value of 2, here's an x value of 5. So we're saying that 5 is not included in the domain, but anything greater than or equal to 2, as long as it's not equal to 5, is in the domain. And so we can express this in interval notation as from 2 to 5, from 2 to 5, union 5 to infinity, including 2, not including 5. So let's go ahead and try and find the domain of our first example, our first composition earlier. So here's a result, 4 over 4 plus x, and those are our two functions, g of x and h of x. So try and find the domain of this composition of two functions. So we're saying to find the domain, we ought to identify the domain of our resulting composition, 4 over 4 plus x, and we also ought to find the domain of our inner function, and we got to look at where the two agree. And so the domain of our resulting composition, right, so we know here that 4 plus x is equal to 0 should be removed from the domain. So any solution to this should be removed from the domain. And so the solution to this is, well, subtracting 4 from both sides, x is equal to negative 4, right? This should be tossed out of the domain. And then also, our inner function is this h of x function. So we need to look at the domain of this function here, h of x. And so here, when is the denominator 0? So here we know that x is equal to 0 makes the denominator 0, and this should also be removed from the domain. Right, so here, our domain of our composition, you can imagine it being x is not equal to negative 4, and x is not equal to 0. And so in interval notation, this reads as negative infinity to negative 4, union negative 4 to 0, union 0 to infinity. So that's the domain of our composition of two functions. So the next thing I want to talk about is decomposing functions. So it's oftentimes beneficial to, if you're starting with a function, to be able to recognize what two functions would be able to compose to the function you're looking at. And so here I've got the function h of x is equal to the absolute value of 1 minus x cubed. And I want to find two functions, f and g, which compose to this function. And the main idea with this is that this function kind of describes a series of steps that you should apply to your input. Right, so this function, it really reads as, cube the input, and then subtract it from 1. Right, whatever you cube, subtract that result away from 1, and then take the absolute value. Right, many functions can sort of be interpreted as a series of steps to apply to your input. And what you can sort of do when you're thinking about decomposing a function is you could break these steps up into one function, an inner function, a first series of steps, and an outer function, a latter series of steps. And so one thing I can do to sort of decompose this is I can imagine, this step here as this first step that we take. I can imagine that being my inner function. And these latter series of steps going in my outer function. And so how would that work? So let's say g is my inner function, and f is my outer function. Then I can imagine writing this as well, my inner function is the cubing function, x cubed, and my outer function is the take away from one function, and then take the absolute value of that. And so, let's check that these work as a decomposition, that if I compose these two functions, I'll get my original function, the absolute value of 1 minus x cubed. And so here, if I take f compose with g of x, well, what we get here is the absolute value of 1 minus, our input, g of x. And so this can be rewritten as the absolute value of 1 minus x cubed. And there we have it, right? That's the result we were looking for. We wanted to find two functions that compose to this absolute value of 1 minus x cubed, and that's what we've done. Another thing I could have done is I could have broken up these series of steps in a slightly different way, right? I could have said, hey, I'm going to make my inner function, my g function, these first two steps. Cube the input and then subtract that from 1. And I'm going to make my outer function this last step. Right, so what I'm trying to emphasize is that there are multiple ways we can decompose a function as a composition of two functions. Right? So here, maybe I'll write it differently. So what if I had written f of x is equal to just this last step. My outer function is just the absolute value of x. Well, I could have also made my inner function g of x is equal to 1 minus x cubed. Right, so here this inner function says cube my input and then subtract it away from 1. Right, the first two steps in our sequence, and then this outer function is just the last step to take the absolute value of our result. Right, and so here, if I check this composition, if I check f of g of x, well, what does this look like? This says take the absolute value of our input, g of x, and in this case, g of x is 1 minus x cubed. So this is another way we can decompose our original function h as the composition of two functions. Okay, so let's go ahead and do some more examples. So I want to find two functions f and g whose composition comes out to be h of x is equal to 4 over x plus 2 squared. And so I definitely encourage you to try this out first. This is one of those topics that it's sort of hard to get a grasp on until you just practice a few times. This is one of those things that you have to go through a few different trial and error examples to get a real good feel of how things work. And so please try this out first, and then we can talk about it together afterwards. Okay, so here, I've got an inner function and an outer function, and here I'm calling g of x my inner function. So, if we have a series of steps here being described by h, the function h, we want the first series of steps to really go with our g of x function and the latter series of steps to go with our f function. And then, again, there's many different ways to break this up, to decompose this function. But here, maybe let's write out a few steps. So here I can imagine h of x as, what happens to our input. Well, first we take our input. Maybe I'll write it as add 2 to our input. That's the first thing that happens in this h function. And the next thing that happens is we square that result. And then lastly, we take 4, and then we divide, and I can't write correctly, we divide 4 by the previous result. And so I can imagine divvying this up in any way I want to make an inner function and an outer function. Here, one way I can do this is I can write, I can have this first step go with my inner function. I can call this my g of x. And then these latter two steps I can use as my outer function, f of x. And so g of x, that's going to be the add 2 to our input function, is that's g of x is equal to x plus 2. And then if f of x does the next two steps, well, it says take our input and square it, and then divide that from 4, right? Divide 4 by that previous result. So here, if these are our two functions, f and g, we can check that f composed with g of x, well, that's equal to 4 over g of x squared, so 4 over x plus 2 squared, and that's, again, exactly what we wanted our composition to be. So this is one way we can decompose the functions. And again, we can rearrange this decomposition, these series of steps up. We can also change this so that our inner function is to the add 2 and the square function, and then this f of x is just the divide from 4 function. And so another way we can do this is we can write f of x is equal to, the divide from 4 function, and then g of x is equal to, the add 2 to our input and then square the result function. When we compose these two functions, we also end up with this 4 over x plus 2 squared. Okay, so I'd like to go over a few more examples just to really practice this idea. So let's take h of x is equal to the square root of 1 plus the square root of 2 minus x. So can you think of a way to decompose this h of x function into two different functions? So here, if I want an inner function and an outer function, and again, I'm gonna use this notation that I've got f of x as my inner function, g of x is my f of x is my outer function, g of x is my inner function. I want this to come out to be h of x. Well, what are the first steps we do in this h of x function? Really, the first things we do is, I can really sort of imagine this part as the first part of the function. Right? Take the square root of 2 minus the input. And then the latter part of the function, I can imagine as adding that to 1 and then taking the square root of the result. And so I can imagine breaking up this function, decomposing this function as my inner function is we'll take the square root of 2 minus the input, and our outer function as taking the square root of 1 plus the input. So this is a natural way we can break up this function as a composition of 2. And so let's go ahead and check that this pans out. So f of g of x, right, this is equal to the square root of 1 plus the input, and the input here is g of x, it's the square root of 2 minus x, so we do get out the same result as our h of x function. And so let's do one last example to wrap this up. So let's do h of x is equal to, let's do x minus 9 raised to the power of 5 plus 3 times x minus 9 raised to the power of 3. So there are a few ways you can sort of recognize an inner function and an outer function. And of course, there's many different things that can work for your decomposition. But sometimes if you see the same pattern appear multiple times in your function, that's also a good indicator that pattern that you see could be an inner function. For example, here we have this x minus 9 appear at two different parts of our functions. We can kind of think of this as we have an inner function of g of x is equal to x minus 9, and that's getting input into the outer function, f of x is equal to, well, x to the power 5 plus 3x cubed. Right, why is this a good example of a decomposition here? Well, if I have f of g of x, well, what I do is I take my input for I take my g of x function as the input. So wherever I see my input variable in f, I replace that with g of x. So here, take x minus 9, and I raise that input to the power of 5. And I take 3 times our input to the power of 3, but the input again is x minus 9. So we get the same thing. We get that same g of x. Or sorry, we get that same h of x. And I want to emphasize that really this is the same idea as what we had earlier, as sort of breaking down our function into a series of steps and using the first for our inner function and the latter for our outer function. And because really when we look at this function here, this h of x function, the first thing you would do when you think about order of operations is you would deal with the parentheses first. And so the first step you would do is you take your input and you subtract away 9 in this first fifth power, and then in this cubed as well, this cube. And so this still works with our previous idea or methodology for decomposing a function. Okay, so to wrap up this video, I'd like to reiterate the fact that decomposing functions is a pretty open-ended idea. Right, we saw earlier that even with one function, we can decompose it in multiple ways. And so really to get comfortable with decomposing functions, I recommend just practicing a few different examples, going through the trial and error experience to see what works and what doesn't. I think it's also a really good idea to try and decompose a function in multiple ways to see what things are possible.